Okay, sir.
Okay, hi everybody. A very happy New Year. So I think we are meeting after a long time. Right, we had a quite of a gap, right? And I hope everybody is doing great, right? So we have 1, 2, 3, 4, 5, 6, 6 of you. Right? Maybe we wait for 2, 3 more minutes. Right? So
Good
what
evening,
happened in
sir.
New Year? Yeah, good evening. Good evening, Hamsini. So what is happening in your school? What is happening for New Year? Anything interesting happened on New Year Day? Did you go somewhere? No. You stayed home only? Okay, fine. So in your school, what is happening, people? Which chapter is going on in your school right now?
Almost going to finish P block elements.
Almost going to finish what elements?
P block elements.
P block. Okay, P block elements. Okay, fine. Fine. So that was the chapter started after. Before that, after your exams, what other chapters were completed?
In school, sir.
In school only, yeah.
Thermodynamics and S block elements.
Thermodynamics and S block were completed. Okay, fine. So we have already completed hydrocarbons, right? And I think you wrote a test also, right? Okay, and today, I think since we completed the chapter, we'll be starting with gaseous state, right? So the flow of topics are going to be in such a way that it is going to be, scientifically, logically, what to say, correct, right? I cannot just start randomly a chapter without knowing the basics of another chapter, right? Because those chapters are connected, as I told, right? So we will be having gaseous state today, that is the states of matter, right? So from states of matter, we'll move on to thermodynamics, and from thermodynamics, we'll move on to equilibrium and ionic equilibrium, right? That will be the flow, right? And after that, maybe we'll move on to inorganic, that is say S block elements, P block elements, right? So all those things will be able to complete, right? So these three chapters, that is states of matter, thermodynamics, and equilibrium, are somewhere related to each other, right? You will actually see the continuation happening in all, like say it's like series, one season, second season, third season, it is going to be like that, right? Okay, right. And a very interesting chapter. Thermodynamics as such is one of the most interesting chapters in all of chemistry you can study, right? Like if it like that too in physical chemistry, right? That is the most interesting chapter according to me, right? Gaseous state, paves the pathway for moving on to thermodynamics, right? Okay, so with that being said, I think we'll start right away. Let me share my screen. Okay, so we are going to start with states of matter for 11th. Okay. Right. So the chapter name is actually states of matter, right? States of matter. But you will in this chapter, say 90% of the chapter, right? You will actually be studying only about gaseous state, right? So we know the three states of matter, right? Solids, liquids, and gases, right? So even though the chapter name is states of matter, right? But we are going to study majority of the chapter actually is given only to gaseous state, right? So the rest, I will not say even 10%, 5% is almost like liquid state, right? I would say this is 95% and 5% is liquids. But again, not so much you'll study, very, very little amount you'll be studying about liquids, because you will study about this liquids and gases, and liquids and gases together actually in fluid dynamics, right? In your physics, you have a chapter called as fluid mechanics, right? So there you'll study in depth, right? What exactly is there, you'll be studying in physics, right? And here we'll be actually dealing with the microscopic aspects, right? Obviously, and in physics we deal with the macroscopic variables, right? How it is moving, what are other stuff, right? In chemistry we deal with the microscopic properties, right? But yeah, there are chapters like for example, thermodynamics deals with macroscopic properties, but we have to start with the microscopic observations, then slowly move on to the macroscopic world, right? That is always going to be the best approach, right? Okay, so as I told, 95% of the chapter is going to be designated to gaseous state, and the rest 5% is for liquid state. And you ask me, sir, what happened to solid state? You have a separate chapter for solid state. The name of the chapter itself is solid state, and that is your first chapter in 12th. Okay, so there you'll study about solid state, right? So in this chapter, we'll be studying about only gases and liquids. All right. Okay, people, right? So we know any matter, right? Coming from Dalton's atomic theory, any matter is made up of these individual particles called as atoms, right? We know that, isn't it? Now, in general, if I have to speak, because matter can again be classified into, okay, first we'll see this, right? See, when I talk about matter, right? Now we know how, okay, people, how do you define what is a matter? Can someone tell me, how do you define matter?
Something that
Anything
has
which
mass and occupies
occupies
space.
space and has mass.
Okay, anything which has mass and occupies space, basically anything which has mass and volume, right, is what is called as matter, right? Good. So this matter can be classified into two types. One are what are called as pure substances, or say pure matter, or other one is obviously going to be mixtures, right? So we have something called as pure and mixtures, right? Now these pure means what? It is going to be made up of single entity, right? Only one type of particle, I can say, right? Only one type of particle can be present in these kind of pure molecules, or say pure matter, I would say, right? So obviously these can be further classified into what, like which is basically based on what is the single entity, right? So if the single entity which you're talking about is going to be in terms of atoms, we tell that these are elements, right? And then if at all you see for them, the single entity we're talking about is nothing but atoms, because we know elements are made up of atoms, right? Okay, and then the other category of pure substances can be compounds, right? Now compounds, we know what is that single entity we're talking about here. Can someone tell me what is the single entity we're talking about in terms of compounds?
Molecule.
Molecules, right? Obviously, right? So many elements combine together to form compounds. So obviously I can say that so many atoms combine together to form molecules, right? So compounds, what is it made up of? They're made up of molecules, right? Okay, these are all our lower class stuff which you already know, right? Okay, now why do we leave mixtures? We study about them also. Now we know that they can be classified into homogeneous mixtures, heterogeneous mixtures. All these things are there. You don't have to worry about it now, right? Okay, now people, this is one way of classification, right? Now another way of classification is, now instead of saying that all matter is made up of atoms, in general we can tell that they are made up of some kind of particles, and these particles can be of three types. Okay, one, it can be atoms, or other things that can be in terms of molecules. Can someone guess what will be the third type of particle which is possible? What is the third type? Atoms, molecules, or it can be?
System.
Sorry? System.
System.
No, not systems, right? Why? Like we are talking about what is matter made up of? Matter made up of system? No, doesn't make any sense, right? Matter can be made up of atoms, or it can be made up of molecules, or it can be made up of, I'll give you last 5 seconds to tell any answer. Okay, surprise, surprise. It is actually going to be ions, right? Say now this compounds can again be classified in two types, right? One, it can be say ionic compounds, or it can be covalent compounds. In covalent compounds, obviously molecules, right? H2O as a single molecule will have again attractive force with another H2O molecule. like that the whole compound stays, right? But in case of ionic compounds, what happens? Now we have another species, right? That is again a chemical species, like say Na plus ion, Cl minus ion. All the ionic compounds will have the cation, anion, and they have some attractive force, and that has some attractive force in neighboring compounds, and that's how it exists. Right? Okay. So these particles, which I'm talking about, can be either atoms, molecules, or ions, depending on what chemical species are we talking about. If we talk about only elements, then obviously we talk about atoms. If we talk about compounds, we either talk about molecules or ion, depending on what kind of compound are we talking about. Right? That is very easy. Right? Okay. Now, any of these things, right, either an atom or a molecule or an ion, actually share some common properties. Okay. Right. So in general, I can say these particles have certain properties, and which are going to be common for obviously atoms, molecules, and ions. What are the three? What are the properties? They have three main properties. Okay. These particles have some properties, right? And as I said, they're going to have three properties. And this also you know, right? Can someone guess what are we talking about here? What are the three properties possessed by particles?
Mass, volume.
That's okay. That is matter. Any matter will have mass and volume. Okay, this is from your first chapter of 10th chemistry, matter in our surroundings. Okay, so we can understand that any particle for that matter, right, between any two particles, right, between any two particles, there will be some some space, right? Between any two particles, there'll be some space, right? Obviously, right? Say this is the atom, right? I mean, so if this is the matter, total matter, right? It is going to be made up of so many number of particles like this. Okay, so you understand that it's not like every particle is like just very, very close to each other like this. No, this is not the thing which what we observe, right? We understand that between individual particles, there is always some space between them, any two individual particles, right? Okay, right. That is the first property, right? Between any two particles, there is always going to be some space, and we call this space as what? We call is there any technical term you can use here? This space is called as
Interparticle.
interparticle space, right? Or if at all you talk about molecules, we talk about intermolecular space, but you're talking about particles as general here, so we call it as interparticle space. This is common, right? Between whether it's going to be this particular particle as an atom or a molecule or an ion for that matter, they will always have some space between them. Okay, right. Next point, between any two particle, right? Ditto, right? That means between any two particle, there is always going to be some kinds of force of attraction, right? Obviously, right? That has to be there, is it not? How is it that the entire matter is, at one place, like solid, like what to say, rigid, something like that? How do we say? Obviously, between any two particles, there should be some kind of force of attraction, right? Or else this will disintegrate, right? And we already know, right? These force of attraction, we even know what are all these force of attractions also. We'll talk about it in a while, right? And these force of attraction between any two particle, right? Can I call it as interparticle forces? Interparticle forces. Right? It can be intermolecular force, interatomic force, interionic force, right? Okay, so that is the second property which is common between any two particles. Like, I mean, whether an atom or a molecule or an ion, right? Okay, and the third and the final property is that all particles, right? All particles contain some kinetic energy. Right, all particles contain some kinetic energy. That means what? You will not see them as stationary things like this. They will actually be moving in some random motion. Every particle that way actually will be moving. Right now, but depending on what state of matter you're talking about, right? The amount of space, the amount of force, the amount of kinetic energy, everything will actually be varying depending on what state of matter you're talking about. That we already know. Right? Okay, so the 3 points are that, like, we have interparticle space, interparticle force of attraction, and all particles have kinetic energy. These 3 points are going to be common for any particle for that matter, right? And based on, as I told you, based on how much space, how much force, how much kinetic energy we have, we will be able to classify matter based on these properties. right? Based on these properties of interparticle space, interparticle force, and how much kinetic energy they have, they can be again classified into solids, liquids, and gases. These are all things which I've been learning from the lower classes, right? Okay, now we know what happens in solid. Solid, the interparticle space is very, very, very small. They are very tightly packed. Say, if at all I can give you a picture, very, very tightly packed, right? Solids. In case of liquids, they are little far away, okay, right? And in case of gases, they are very, 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 very far away from each other, right? Okay, that means the space is going to be increasing this way. And the same goes with your force of attraction. I don't have to tell about it, right? Solids have the strongest interparticle force, liquids have intermediate force, and gases have almost very, very minimum amount of force of attraction between your individual gaseous molecules or gaseous particles, right? Okay, talking about kinetic energy. Kinetic energy, obviously, wherever I don't have much force, wherever I'm feeling little free, there I'll be able to move easily, and therefore more kinetic energy, right? So we can obviously say gases are the ones which are going to have the maximum kinetic energy, right? And the solids are the ones who are going to have minimum kinetic energy, almost zero, even we can say. But again, we will talk about it when it can be zero. Actually, in this chapter in thermodynamics, we'll try to understand that, right? Okay, so by, as I told you, based on the amount of space, amount of force, amount of kinetic energy, solids, liquids, and gases, right? That we know. Okay, right. Now among this, right, these actually gases are going to be very special, right? Gases are going to be very, very special. Now, why are they special, right? We'll look into it, right? So gases are special because, right? Because they occupy whatever volume you give them, literally, right? They occupy whatever volume you give, Is it not? Say you give only this much space, the gas will occupy that space. If you give it an entire room, it will occupy the entire room. If you give it the entire universe, obviously it is going to occupy the entire universe, right? So that is actually making gases very, 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 very special, right? Okay. And second thing is, gases are the ones which can be easily converted into the other two states, right? That means gases can be easily converted to liquid phase. And you can also see that gases can be easily converted into solid state in some cases, right? But liquid again has that property, right? But again, liquids are incompressible, right? We know, right? When I have say some liquid like water, right, and if I try to push, right, actually you will not be able to push. Ideally speaking, theoretically speaking, you will not be able to push the piston down, right? If at all you try so much, eventually what will happen? This parts will break, and eventually water will start falling out, right? Okay, so that's the reason we say liquids are actually almost incompressible. Solids are compressible. Gases are very highly compressible. Is it not? Another very important point is that the gas is going to be very, very, very compressible. We can actually do a lot of stuff with this compressibility, right? Lot of engines, lot of other equipments actually work on this particular property that gases are very, very, very compressible. Even though they might not go to liquid state, but still you will be able to compress them to a maximum extent, expand them to some extent, right? All these things actually make gases very special, right? Okay, right. Now, so as already said, right? So this chapter is going to be majority only about gases, right? So and we even understood what are some special properties only gases have, right? The solids and liquids will not have, right? Or a combination of solids and liquids properties can be present only by gases. Those kind of things are there, right? And one more important thing is that if at all you if you ask me which particular state of matter can be easily studied, right? Again, it is going to be gases, right? You will see that in this chapter in thermodynamics as well, you will actually see only most of the cases we'll be using only gases for our experimentations. Okay, it is because it is very easy to study them, right? The change in property, for example, say I increase the temperature, I have a gas molecule, right, and I increase the temperature. Now the gas will expand, right? Now actually I'll be able to visualize something, right? I'll be able to measure something which is actually happening by changing some other variable, right? Now these kind of things are very much, it's not like it is not going to happen in solids and liquids, but the amount of change which you see is enormous in case of gases. With small change, you will be able to have a very big consequence happening in gases, right? That might or might not be possible in case of solids and liquids, right? So chemically speaking, right, if at all you want to study a particular thing, right, making them into the gaseous phase and studying them actually makes more sense, right? That is again the overall picture you can understand, right? Okay, so with that being said, we'll move on to the like say we have some variables which we have to look into, right? When we want to study about gases, obviously we're going to study about gases in this particular chapter, right? There are going to be theories coming up, there are going to be other explanations, laws, all those things are going to be there, which like basically different scientists studied about different properties of these gases, right? So there are the laws in their names: Boyle's law, Charles' law, Gay-Lussac's law, Avogadro law, right? Ideal gas equations, Van der Waals equations. So all these things, the Graham's law of diffusion. So you understand, right? A lot of scientists have actually worked, very like obviously very long back in 1800s, 1700s, right? So they have actually produced so many results, and those results is what you're going to study about these gases scientifically, right? We already know what are the small say basic things about gases. Now we're actually going to dwell into it, right, and study what exactly is there, right? So if at all I want to study about them, measure them, do something with them, we have to understand that what and all are the things which you actually can vary in a particular gas, right? And those things which can vary are what are called as variables. Okay, right? Now these variables we are going to study, right? What and all are the things you can make with the gas? What can you increase? What can you decrease? What can you double, triple, make it half? What and all are things which you can change in the gas? Right? You already know the main variables which can be changed with respect to a gas particle is these three things, right? Pressure, volume, temperature, right? You will be able to compress the gas by increasing pressure. If you compress the gas, the volume will decrease. Say, for example, when you heat a gas, the expansion happens, right? These and all are the common observations you'll be able to see with the naked eyes. You don't have to go use a microscope. Okay, pressure is changing, temperature. We don't need all that. Just by looking at it, just by using a small thermometer, just by using some gauge for pressure gauge, or say volume, we can even see with the help of the measurements there. So these are the variables which you'll be able to easily sense that they are actually changing with respect to gas, right? So it is very important for us to study them in depth, right? We will understand what exactly is pressure. We know, right? But still, like little more aspects which you might or might not know, right? Those things we'll see. What are the different units which are used in day-to-day life? Whenever if you're going to become a chemist or a physicist, right? What are the different units which you have to know for you to take some measurements, right? And those are things you have to study about this pressure, volume, and one more thing also, which you already know a very good sense of. Another thing is number of moles, the amount of gas, obviously, right? So that is also we are going to study here. Not again, we already know quite a bit about number of moles in the first chapter, some basic concepts of chemistry, right? So, but again, we will see that how this number of moles, if at all it changes, how these things changes, or interrelations, like how pressure and volume are related, how volume and temperature are related, how pressure and number of moles, how volume and number of moles are related, right? Between these variables, if I change one of them, how the other thing changes, right? That interrelationships you are going to study in this chapter, right? So obviously for us to appreciate, study all those things, we have to know what exactly are these quantities. Is it not? Right. Now let us talk about pressure. Right. Now, what exactly is the pressure? Like pressure of a gas. Okay, we are talking about pressure of a gas. Right. Now, what do you mean exactly? What is that logical meaning of this pressure of a gas? Right. Now we will try to understand this. Right. You already have some picture. I think if I just start explaining it itself, you will understand, because you should have already studied this. Okay. Right. Now we understand that there are so many gas particles in a particular a vessel, or say a container, whatever it is, flask, whatever it is. Okay. And we know that these individual gas particles have kinetic energy, right? These individual gas particles have kinetic energy. That means they'll be moving in random directions. Okay. Now, when they're going to move in these random directions, they will definitely undergo collisions, right? Definitely not, right? Because now when one particle is moving like this, another particle is moving like this and like this, they will definitely collide, right? So there can be two kinds of collisions. Okay, the collisions we're talking about, one kind of collision you understood, collision between two gaseous particles. Yes, definitely possible, right? Now, another possibility is that these individual particles will go and hits the walls of the container, right? That is another kind of collision you can have. Is it not, right? Collision with one gaseous particle and the walls or the boundary of the container, right? Now, that is another kind of collision you can expect, right? One between two gaseous particles, and another kind of collision which is between the gaseous particle and the walls of the container. Okay, now this pressure is actually arising due to collision between the boundary and the gaseous particle. Okay, now it is very easy to understand, right? Now instead of this particular surface, you just keep your hand. Okay, like maybe you make a this thing with your hand, some kind of box with your hand, and you trap a gas. Okay, right. Now, if at all there is enough amount of gas, you will actually see that the gas molecules are actually pushing you, pulling you, pushing you like this. So they will try to expand actually because they have so much kinetic energy. As I told, whatever volume you give, they're very greedy. Whatever volume you give, they're actually going to take it up, right? So they always want to expand because you will understand, right, that gases getting expanded under certain condition. There are a lot to study about it. Okay, like there's not one thing special I can tell about it. Everything about gas getting expanded is actually very special. You will study about this more in thermodynamics. Even in this chapter, you will study, right? Gases always want to expand, right? Okay, so what I'm trying to tell you is that because of this collision, right, these particles they are moving with some momentum, right? So obviously, if they go hits the walls of the container, there will be some momentum transfer, right? There will be with some force that is going to go hit the walls of the container. Right now, let us zoom up, right? Let us just zoom this part alone here, right? Now, there will be some area, right? This has this particular point of contact when the gas particle hits this particular area, right? This particular spot in the walls of the container. Let us just zoom that and look into it, right? Now, what is happening to the surface? The entire gas particle is coming and actually hitting here. The zoomed effect, I'm telling you, right? And this will hit with some force. Right, this will hit some with some force, right? And you understand that this particular entire area is actually getting affected, right? So this force divided by the area of contact, right? The force which is with which the particle is hitting divided by the area, how much area there's contact between this particle and the gas and the surface and the boundary, right? That area, this particular term, right? F by A is nothing but the pressure of the gas. Right, how much force it hits, right, with which it hits, divided by the area of contact. That particular mathematical value is what is the pressure of a gas, right? That is the very basic. I think you already know this also, right? You must have studied this in your 10th class maybe, right? So this is what is the pressure of the gas. This is how gases exert pressure. Okay, someone wants to ask something?
Sure, so this is internal pressure of gas.
Yeah, this is the internal pressure of the gas. Obviously, for if at all, this is an isolated system. Okay, for those of you who study thermodynamics, right, you should know what is an isolated system. Isolated, nothing I'm going to do, right? Just undisturbed, and that's a container. Inside the container, some amount of gas is there. That's it, isolated. Okay, so obviously, the only pressure which you will be able to expect here is the pressure of the gas. That is the internal pressure of the gas. If you want to call it that way, yes. Okay. Right, so that is about pressure. Okay, now what are the different units of pressure? Right, first of all, what is the SI unit? Understand, right? SI unit of pressure is very understood because P is equal to F by A, right? So I know for F it is Newton, right? The SI unit of force is Newton divided by area. Area's SI unit is meter squared. So remember that the pressure's SI unit is Newton per meter squared. Okay, the pressure's unit is SI unit is Newton per meter squared, or this Newton per meter squared can also be called as Pascal. Okay, the unit is PA. Okay, right? You can tell 1 Newton per meter squared, or you can write 1 Pascal. Both of them remains. Both of them means the same. Okay, so what is the SI unit of gas? SI unit of pressure? It is either going to be Newton per meter squared, or it can also be called as Pascal. Right, these two are the SI units of pressure. Okay, now what are the other units? Right, commercial units we say. Right, how commercial units of pressure. Right, different units are there. Right, so another thing is ATM. right? ATM is nothing but atmospheric pressure. Atmospheric pressure. Right? See, for every unit, you will actually have a history, you will actually have an explanation, how they came into the picture, how is it that a particular number is coming up, all these things, but you really don't have to worry about it. Okay, right? After a point of time, it actually becomes very boring, right? What is this? So many numbers coming up. Don't worry about it. I am directly going to give you how are these units are directly connected with now what number if you put now. Okay, you will be able to convert ATM to Pascal, Pascal to ATM, something like how do you do this? That we will see, right? But what is the history? Why is it called ATM? Why exactly this particular number only? You don't have to ask me this question. If you're really interested, please go on. Please go study ahead, right? You will actually get the ideas, right? If you just Google it, very, very simple. Right. Okay. So the another thing is ATM, as I told, atmospheric pressure. Right. Now, what you have to understand is, people, one atmospheric pressure is 101,325 pascals. Okay. Right. One atmospheric pressure, one ATM is 101,325 pascal. Okay. Fine. Now, you can also approximately say this as 10 to the power 5 pascals. Okay, approximately. Right, one ATM is 10 to the power 5 pascals. Okay, right, approximately. Obviously, the exact value is 101,325 pascal. Right. Next unit about the unit of pressure is mm of Hg. Okay, mm of Hg. Right. Now, actually, I have to talk about this, okay, because mm of Hg, we generally use for volume, right? But here somewhere in pressure also we are using this mm, right? Not even mm is often not volume, right? It's actually length, millimeter, right? So how is it that a length is used in pressure, right? What exactly are we doing here? We have to understand this, okay? This really needs some explanation for you to appreciate. Okay, people. The first instrument which was actually developed for measuring pressure, okay, which was the first instrument, or say a device which will be able to measure pressure, those are what are called as manometers. Okay, one R only, right? Manometers. Okay, now there are different versions of manometer nowadays available, right? But a simple one we can understand. Okay, simple one. Okay. Look at this. Okay, I'm thinking how to draw this. Okay, fine. So we have one gas here. Okay, now no, it shouldn't come like this. Yeah, it's like this only. Okay, please bear with my diagram. Okay, please. Okay, and here it is closed. Okay, here it is closed, and this entire thing, like maybe use red color, some other color, black. Okay, now this entire thing, right? Okay, there is a tap. Okay, now here there will be a tap. This is the tap, right? Okay, okay, fine. This, okay, from here we'll speak. Okay, this entire thing, right? This black color thing, entire till here. Okay, I don't think it is still here or not. Okay, fine. Here till here is fine. Okay, fine. So till this point, from this point, this entire thing is mercury. Okay. Okay, so mercury, generally mercury is what is used, right? Okay, fine. So now here in this place, there'll be one inlet and all, and you will be able to put the gas inside, whatever gas you want to measure the pressure for, right? Whatever gas you want to measure the pressure for, you will be putting it inside this particular bubble. Okay, then what you do, you open the tap. That's it, you open the tap. Right now, what is going to happen? This gas is going to travel. It will have some pressure, right? Now, because of this pressure, say initially, if this was the level of mercury, right? This is H1. Okay. Now the mercury level will drop, right? The mercury level will drop here to say H2 because of the pressure of the gas, right? As the gas will tends to move here, it will have its pressure that will push the mercury down, and obviously this side it is going to go up. Say initially here only, like if I can use right? Say initially here only the H1 was there. Now it would have actually moved to this particular point H2. I mean, I'm talking about the two different sides. Maybe you can call it as H-1 and H-2. Here it is normal H1, H2. Right? So you are easily understanding, right? If because of the because of the pressure of the gas, right, you're actually seeing that the length of the mercury column changes, right? So obviously you will be able to have some measurement here. You'll be able to have the millimeter measurements here. Okay, here also millimeter measurements. So with the help of this change in height, right, how much change in height happens, accordingly I can tell, can I tell that the pressure is directly proportional to the change in height of the mercury column? Is it not, people? Right? Pressure in this case, you can easily understand pressure of the gas, right, is directly proportional to how much increase or how much decrease. I mean, obviously how much increase is going to be there in the height of the mercury column. Is it not, right? And then is this not very easy? We already know one relationship between pressure and height. Can someone tell me pressure and height, how are they related? There is an equation, right? It is actually coming from here only. Whatever the thing which I'm going to explain, you understood that the pressure of the gas is actually directly proportional to the change in the height of the mercury column or change in the length of the mercury column, right? So from this only, we have a beautiful equation for pressure. Pressure is equal to rho g h, right? This h is nothing but delta h. Okay, right? What is this rho? Can someone tell me what is this rho, people? Pressure is pressure of the gas. Rho. Is this don't tell me that this is the first time you're seeing this equation. I don't believe it. You must have seen this before in your physics 10th class. Somewhere you should have seen this. What is this rho?
Density of the gas.
Yeah, yes. This is density of the particular liquid. In this case, it's mercury, right? You can use any liquid here, right? But why are we specifically going for mercury? With the help of mercury, the change in height can be easily visualized. The change in height for a small change in pressure is huge. Okay, but other liquids will not have that much change. Very small changes in height will be there. You will not be able to see them. So that's why we go for mercury. Till now also, in thermometers also, we understand, right? Small change in temperature, now high change in height for mercury. That happens. Okay, so this rho in general is the density of the liquid we're talking about. Okay, which liquid you're using for change in height. And this g is obviously acceleration due to gravity. Acceleration due to gravity. Okay, and this height is the height of the column. That is easy. Height of the column. Change in height, if you want to tell it like that. Okay, guys, 1 second. I have to plug in my power. 1 second. Let's see, where is it? Light. Okay, so again we got a beautiful equation, right? We actually saw that the pressure is actually related to the height of the mercury column or height of the liquid column in general, right? And obviously you understand from here itself that the pressure and height are directly proportional. These two are constants. Okay, rho and g are nothing but constants. Okay, right? So if at all I put the value of, in this case density of what I'm talking about, mercury, right? We said, look at this. We said that, right, mm of Hg is also a unit of pressure. How? We understood, right? As the change in the manometer level, the height of the mercury column, the pressure will be changing. Okay, so what they understood is if I make it open, okay, if I make a thing like this, look at this. Okay, this side it is closed. Okay, fine. Now this side it is open. Okay, right. Now what we generally say, we say that it is open to atmosphere, right? This is atmosphere, normal atmosphere. Okay, now we know what is the value of pressure for 1 atmosphere. right? We know what is the pressure of atmosphere. We know that it is 1 atmospheric pressure, 1 atm, right? At ground level, at sea level, we say that the atmosphere will have a pressure of 1 atmospheric pressure, 1 atm. Right now, this pressure, whatever is exerted here, right, on the mercury is nothing but 1 atm. Okay, right. Now, what they understood is that because of this pressure, because of the pressure of 1 atm, again there will be some change in the mercury column. Okay. Now, what they understood is that for 1 atm, right, for 1 atm, actually they understood that there was 760 mm of Hg was actually changing. Okay, so this is the relationship which you have to understand. Okay, so where are you? Pressure? Yeah, so we understand that 1 atmospheric pressure is equal to 760 mm of Hg. Again, a very, very, very important relationship. Okay, 1 atm is equal to 101325 Pascal. And again, now 1 atmosphere is equal to 760 mm of Hg, or you can even write it as 76 centimeter of Hg. This is also fine, no issues. Okay, 76 centimeter of Hg or 760 mm of Hg, 1 atmospheric pressure. Okay, right. This mm of Hg, okay, this mm of Hg is also called as torr. Okay, is also called as torr. So I can also write 1 atm is equal to 760 mm of Hg, that is also equal to 760 torr, because mm of Hg and torr are nothing but equal, right? 1 mm of Hg is 1 torr. Okay, so this and this can be directly connected again, right? So 1 atm is equal to 760 torr or 760 mm of Hg, right? Okay, now anything else is there? Yeah, one more thing, that is Pascal, Newton, and bar, right? Okay, now another last unit which you have to know, right, is 1 atm is equal to 1.013 bar. Bar is another unit of pressure. Okay, bar comes from barometer. Barometer is actually the instrument which is used to measure pressure. Okay, so the unit the unit of pressure in which the barometer measures is actually in terms of bar. That's a separate unit. Okay, don't worry about it. Right, it comes from barometer. Right. Okay, so another unit of pressure that is connected here is 1 atm is equal to 1.013 bar. You can also approximately say that as 1 atm is approximately equal to 1 bar. Okay, because 1.013 can be approximated as 1 itself. Right. So what are all the different units of pressure, people? Right, we have Pascal or Newton per meter squared, that is SI unit. Right, after that we have atm, we have mm of Hg or torr, right, or we have bar, right? So these are all the different units used for pressure. They have their own uses, right, depending on what kind of application we're talking about. Right, if not we're talking about atmospheric pressure, then we talk about atm, that means in terms of atmosphere. Right, if at all you talk in terms of cyclones, right, cyclone, we say that on this much pressure they have, something like that, they generally talk in terms of bar. Right, and then you go for physics. Generally, if at all you actually go for some say water, for example, in the case of liquids in general, we go for this pressure Pascal in the, for Newton per meter squared. So like that, we'll be different areas of research, different areas of requirement, we use different units of pressure. Right, and all those things you have to know, people. You have to know all these conversions. If you don't know, you cannot do problems. Right, these things would be there in your fingertips, all the conversions which I gave now. Right, so that is all about pressure which you have to know. Right, okay, moving on to volume. Right, now volume, you know what is exactly the volume, right? The space occupied. How much space that particular species or particular matter occupies is what is called as volume. Okay, very simple. Right, now we don't have to speak much about the volume. We know that whatever volume you give, right, whatever volume you give, the gases will occupy that volume. No, don't, like if at all you give this small space or you give this small space, same amount of gas only, but it will be very much expanded like this. Okay, right, so that is I think that is a very special property of being a gas. Okay, right, now what are the different units of volume? First, if I talk about the SI unit, SI unit is, can someone tell me what is the SI unit of volume? Liters, right? Is it liters? Guys, what is the SI unit of volume? Really? Nobody knows what is the SI unit of volume. Okay, I am telling you that the SI unit of volume is liters. Just type in your chat box yes or no. True or false. SI unit of volume is liters. True or false. Type it in a chat box. I'm looking in the chat box. Yes, please go on. Type. The SI unit of volume is liters. Okay, Ashwat says no. Sri Girda says no. Okay, come on, everybody participate. We have almost 11 people here.
No, sir.
Okay, fine. Another no.
Yes,
Fine.
sir.
Okay. Oh, so Pradeep says yes. Okay, Ganesh says no. Okay.
Sir, isn't it meter cube?
Correct. Yes, that's what. When I ask you, then what is the SI unit? You should tell, right? That's meter cube. Correct. Right.
Sir, area
So
is
people,
meter square, so volume will also be meter cube.
exactly. Area is meter square. Definitely, volume will also have meter cube. Yes. Okay. So SI unit of volume is meter cube. Okay. Right.
So,
then the other units you can have. Right. Then the commercial units.
sir.
Yes, Kanna.
Sir, but then 1 meter cube is nothing but liter only, right, sir?
No, 1 meter cube is 1000 liters. Okay. Well, we'll see the conversions now. Don't worry. Right. 1 decimeter
1
cube is 1
centimeter
liter.
cube.
Exactly. 1 decimeter cube is 1 liter. Okay. Fine, people. Like we'll see all the conversions here now. Right. Fine. Now, if at all I want to connect your liters with meter cube, please understand that 1 meter cube is 1000 liters. Okay. This is the first one. Right. 1 meter cube is 1000 liters and 1 decimeter cube is 1 liter. Okay, right. And 1 centimeter cube is 1 ml, milliliter. Okay, 1 centimeter cube is 1 ml, and obviously 1000 ml is 1 liter. Okay, so these are all the different things which you have to know. Meter cube, 1 meter cube is 1000 liters, 1 decimeter cube is 1 liter, 1 centimeter cube is 1 ml, or you can also write it as 10 to the power minus 3 liters. That is also okay because 1000 ml is 1 liter, right? So all these are the different units generally used for volume. In your problems, accordingly, you have to use them, right? Okay, so that is about volume, right? Very simple. Next, the last thing is temperature. What is temperature? Right, you will study about temperature in depth in your thermodynamics chapter, but here I'll just give you an overcap, little there and there will be able to study. Okay, so in layman language, right, we can explain or we can define temperature as a measure of hotness or coldness of the body. I mean, hotness or coldness of the particular substance, hotness or coldness. It's a measure, it's a number by which you will be able to tell, okay, this is hot, this is this cold, this is this hot. Right, giving some value to the hotness and coldness is what is temperature. Okay, right. Now that is a very low, like say, for as I said, it's a layman explanation. Right, you will exactly study what is temperature and how is it operating and stuff in thermodynamics. Okay, right. Now with that being said, the units, right? Again, the SI unit of temperature. People, what is it? Temperature, SI unit.
Kelvin.
Yes. Right, SI unit of temperature is Kelvin, capital K. We give the symbol, right? Okay. Other than that, we have the commercial units. Right. So commercial units, we can have Celsius degrees, right? Celsius degrees, and we have another thing is Celsius Fahrenheit. Okay, now Celsius degrees can be connected to the Kelvin like this, right? So if at all you have the value in Celsius degrees and you want to convert it into Kelvin, what do? Right? To the Kelvin, I mean, if you want to get the Kelvin value, right? So all that you have to understand is 0 Kelvin, not 0 Kelvin, 0 degree Celsius, right? 0 degree Celsius is 273.15. Okay, I'll give you the exact value, right? So 0 degree Celsius is 273.15 Kelvin. Okay, right. So that means if I have the value in Celsius degrees and I want to convert it into Kelvin, you have to take the Celsius degree value and add 273.15 Kelvin. Okay, right. Next, if at all you want to convert Kelvin to Celsius degrees, okay, now what you have to do? You have to you want the value in Celsius degrees. Okay, and what you have to do? You have to take the Kelvin value and subtract 273.15 Kelvin, 273.15 to get the value in degrees Celsius. Okay, right. For example, if I say it is 100 degrees Celsius, then I can tell it is nothing but 373 Kelvin. Something like this. Very simple, right? Like, what did you do? You added 273 to this, so it becomes the Kelvin value. Okay, so like this, we'll be able to do the conversion. Okay, fine. Next, what about Fahrenheit? Now remember that if you want the value in Fahrenheit and you have the value in degree Celsius, it's very simple. 9/5 into the degree Celsius value plus 32 is what is the conversion between the Fahrenheit value if you want to get, and you have the value in degree Celsius. How do you convert it into Fahrenheit? This is how you convert. The degree Fahrenheit is equal to 9/5 degrees Celsius plus 32. Okay. Right, cool. So with that being, what is the time, people? Okay, do you know that this is going to be a 2 hours class, people? Did you know that this is going to be 2 hours class?
So it was 2 hours, right? Always.
It was like, no, when before your first term we actually had only 1.5 hours, but after the midterm we started doing it as 2 hours. So like this class
so
is
like
2 hours.
after when the second term started, sir informed that it's 2 hours.
It's 2 hours only. Okay, good. Then good. Right, fine. So that is about your temperature also, right, people? Okay. So we know about now pressure. What exactly is pressure? What are the different units of pressure? What is volume? What are the different units of volume? Temperature and its different units. Right. Now what are we going to do? We are going to study the relationship between them. I am going to take 2 variables at a time. Okay, I'm going to take, say, pressure and volume, right? And I'm going to keep the temperature constant. Okay, what I'm going to do? I am going to take pressure and volume, right? I'm going to make temperature constant. Okay, now when I increase pressure, I'm going to see what is going to happen to volume. When I decrease pressure, what is going to happen to volume at one particular temperature, 25 degrees Celsius. At that particular temperature, I am going to do this process, right? The relationship between pressure and volume, how they are changing with respect to each other at some constant temperature. Okay, now we are not going to do this, people. These observations have been already done by your wonderful scientists before you, right? So we are going to study their relationships in the form of the law, and the law's name would be obviously or based on whichever scientist discovered the law, right? Okay, so now what are we going to do? We are moving on to relationships between pressure, volume, temperature, and the number of moles. Okay, we are going to study the relationship between them, right? Okay, under that, the first law which we are going to study is Boyle's law. Okay, Sir Boyle, right? Boyle's law. Okay, please take it on the statement, people. I'm going to give you the statement. Please take it down. It states that at constant temperature, it states that, comma, at constant temperature, comma, the pressure of the gas is inversely proportional, right? Is inversely proportional. The pressure of the gas is inversely proportional to the volume of the gas. To the volume of the gas. Right? Okay, so if I read the statement entirely now, it states that at constant temperature, the pressure of the gas is inversely proportional to the volume of the gas, right? Okay. So if I have to give you the mathematical relationship, can I tell that the P of the gas is inversely proportional to the volume of the gas? And even though Boyle did not say this, people, we have our own common sense and we understand that this is actually what is happening in reality, isn't it? Right? It is actually not a, like, it is, rather than calling it as a law, it is nothing but an observation, right? Observation that smart person was able to, and all our dumb people at that time were not even able to make this simple observation, right? That's how I see it. Okay. So what happens here? We have a gas, right? This is the gas, okay, and this is a piston, right? So now when I increase the pressure, what is happening? The volume is actually getting decreased, right? This is the volume. Now initially this entire space was the volume. Now only this much is the volume when I increase the pressure. That's very simple to understand, right? So pressure and volume are inversely related. That is what it says, right? So now, if at all I want to remove a proportionality sign, I'll bring in a constant, right? So P is equal to K by V, or we can write some PV is equal to constant, some constant K, right? The pressure, the product of pressure and volume of a gas is always going to be one constant value, right? So we can even write it like this, right? P1 V1 equal to P2 V2 equal to P3 V3 equal to so on so forth, Pn Vn, and all these products, all these individual products are equal and they will be equal to some constant value. That's very simple. Okay, right? Fine. So that is how the pressure and volume are related. Yes, go on.
Sir, how can pressure change at constant temperature?
How can pressure change at constant temperature? Why not? Right? Say now this thing is there, right? This entire piston arrangement. Okay. Now I keep it, right? I keep it in a temperature bath. Yeah, I'd say this is some hot water. Okay. Somehow I make sure that the hot water temperature is only 30 degrees Celsius, not more than that. I'll be able to maintain this. No issues. That is not a big deal for me. I'll be able to measure the thermometer. And if at all it becomes cold, I had to add more hot water or some mechanism I can have so that I'll be able to maintain the temperature, entire temperature to be only 30 degrees Celsius. And at this temperature, now I'm going to increase the pressure. The piston is going to be here. Yeah, I have changed the pressure, right? At constant
Sir, but if pressure is changing, then temperature should also change, right?
That's what we are making sure that even though the pressure is changing, the temperature should not change. We are outside making it sure. That's why we are there, right? So we are going to make sure that even if the pressure is increasing or decreasing, the temperature obviously they will change, right? That is how nature works. But we are going to go against the nature. We are going to make sure that irrespective of this change, right, the temperature is not going to change. Only the volume will change. Okay, that is what we are trying. That is what we are doing. We are doing from the outside. We are making sure that the temperature is constant. Yes.
Okay.
Right. So yeah, these are all the mathematically you'll be able to understand any of this. Right. Say for example, people. For example, if I find that the constant value is say 12. Right now, what and all are the different pressure and volume values? Right. Say for example, pressure, volume, P into V, right? So if I tell that one of the cases the pressure was 12, say the possibilities can be 2,6, right? Another possibility can be say 6,2, right? Another possibility can be say 4 into 3, right? Another possibility is 3 into 4, whatever the different values of pressure, and at that pressure you measure the volume, right? Those two values, if you multiply, you have to get the same constant value. Okay, now ask me, sir, in reality, is this going to happen? No, people, no. Okay, these are ideal conditions. You will actually see we are actually studying about a gas which does not exist in this universe. We are actually studying about something called as an ideal gas, perfect gas, right? So that how, okay, what are the what are the qualities possessed by the gas in order to be called as perfect? That we'll understand. Okay, that we'll understand slowly. One of the condition is this. Okay, that first condition for a gas to be a perfect gas, right, is it has to follow Boyle's law strictly. It has to follow at all temperatures. Okay, right? But you will see that no, it is actually not going to happen, right? Because none of the gas in this universe, none of the gas in the reality is actually going to obey this particular law, or any other condition which is going to come for a perfect gas is not going to get followed in reality. Okay, right. But now given these guidelines to us, okay, this is how a perfect gas look. If it's there, it's very easy to do the measurements and stuff. So sometimes we assume that the gas is actually an ideal gas, and we actually go for some mathematical relationships like this. That makes the job easier, even though not accurate, right? But some kind of linear relationship you'll be able to get. Right? In order to solve a very big problem, these small assumptions actually doesn't matter much. Okay. Anyways, right? So that is what is called as Boyle's law. Okay, people, right? Pressure and volume are inversely related. So P into V is a constant. Right. Now the same thing graph, right? I will be able to see in the form of a graph. Right? If I plot a graph between pressure and volume, right? We understand that as pressure increases, the volume should decrease. So you will get a graph like this. You can understand, right? As the volume increases, the pressure actually decreases. That's exactly what is happening. Okay. So whenever there is a gas and you take different, this is one pressure, this is one volume, second pressure, second volume, third pressure, third volume, like this. Okay. If you're going to plot a graph, this kind of graph is the shape of the graph is what is called as a rectangular hyperbola. Right, the shape of the graph, these kind of graphs, right? These are what are called as rectangular hyperbolas. They will never touch the axis. Okay, if you see, even if you go to infinity, right, they will just go close, but they will never touch the axis. This also, this is going to never touch the axis, x-axis or y-axis. Okay, now these kind of things are what are called as rectangular hyperbolas. Okay, and this is the type of curve which you get if you plot between pressure and volume. Okay. Right. Now, before we take a break, people, right, I'm going to give you a question. Ponder over this question, right? Fine. So we have one graph like this, another graph like this, and another graph like this. Okay. Now, these, okay, people, right? Remember, okay, whenever we do a process at constant temperature, okay, whenever we do a process at constant temperature, those kind of processes are what are called as isothermal processes. I think you should have known this from thermodynamics if some of you have studied, right? An isothermal process is where we maintain one constant temperature. Okay, right. Now the isothermal process we understood, right? Now this graph, whatever I'm expecting, the PD graph, whatever I'm expecting, that graph can be called as something as an isotherm. Right, the graph. What is the isotherm? Isotherm is a graph, right? Graph which is obtained at one constant temperature. That's it. Okay, isothermal process is that particular process. Okay, whatever is happening, isotherm is the graph which we get out of it in that at constant temperature. Okay, right. So these three which I have drawn here are three different isotherms. Means this was done at one temperature T1. This was done at temperature T2, right? Entire process. And this graph was obtained when the temperature was T3, all constant temperatures, right? So three different graphs you will get. Okay. So now tell me which is higher, which is greater. T1, T2, T3, we should put the greater symbol or lesser than symbol. What is the relationship between T1, T2, 3T, which is greater, which is lesser, right? That is what I wanted to think about, right? And with that, we'll go for a break, right? Time is almost 6:03. We will meet by 6:15. Okay, right? We'll meet by 6:15, right? So I'm gonna mute myself, right? And I'm gonna switch off my video and I'll be back in almost 10 minutes, right? Okay. Hi guys. Are you guys back? Will we start?
Yes, sir.
Okay. Share my screen again. Right. Okay. So before we went on the break, right, I told you that these are what are called as isotherms. The graph which you obtain at constant temperatures are what are called as isotherms, right? Okay. Now we have three different isotherms here obtained at three different temperatures, right? I asked you to find which one is greater, which one is lesser. Any ideas? Can everybody put their answers in the chat box? Doesn't matter whether it is right or wrong. Just put T1, T2, T2, T1 greater than T2 greater than T3, or say T3 is greater or T2 is greater, whatever it is, whatever you feel, right? Whatever you feel is the order, just put them in the chat box. Go for it, and I'll check it. Okay, just a guessing game. Don't worry about whether it is going to be correct or wrong. No one is going to judge you. Please go for it. What do you think will be the answer? T1, T2, T3, which is greater, which is lesser, which is in between? Okay, one answer is there. Shreyan says T3 greater than T2 greater than T1. Okay. Sri Girdha says T1 is the lowest. That means same answer as Shreyan. Okay. Then, okay, Subrajit says the same thing. T3 greater than T2 greater than T1. Okay. Anybody else wants to contribute? T3 greater than others. Okay, Hamsani says the same answer. Okay, fine. Right. Okay, so let us investigate. Right. Let us see what exactly is the answer there. Right. People, whenever these kind of things are given to you, right, I would always tell take one constant value and vary the other one. In the sense that, for example, look into this. Right. We can take, maybe actually I'll draw a little more straight line graph, and then that will be better. There's something wrong with the, okay, right. So, okay, fine. This is 1, this is 2, and this is 3. Okay, fine. So what we do is we will take, this is pressure, this is volume, right? We already know, right? So what we'll do is we will take one particular pressure. Okay, we'll take one particular pressure and we will take the corresponding volume in this graph. So this is V1. Okay, this is T1, right? T1, T2, and T3, right? So the volume which we get here is V1. Okay, right. The volume which we get here is V2, right? And the volume which we get here is V3. Okay, right. So V1 corresponds to T1, V2 corresponds to T2, and V3 corresponds to T3. Right. Okay. Now from the graph itself, we know that this side the volume increases. So I can tell for sure that the V3 is greater than V1, V2 is greater than V1, because this side the volume increases, right? The graph, very simple to understand. Okay, right. Now we know that, say there is a balloon like this. Okay, now there is some gas inside, right? Now if I heat the balloon, what will happen? Right, the balloon will become bigger, right? The balloon will become bigger, right? So what is happening? Actually, this is going to be another law which you will study, that the temperature and volume are going to be directly proportional. Obviously, right? On heating, the gas expands, right? So if we understand that the V3 is the greatest and V1 is the least, so I can also tell that T3 is the greatest than T1 and T1 is the least, right? And whatever the answers which all of you gave are absolutely right. Okay.
Sir,
Yeah, tell me.
sir, in the same case, but what if we take a constant volume?
We can do the same thing. Okay, we'll do the same thing now, right? Look at this. Okay, 3 graphs. Okay, so this is pressure, this is volume, T1, T2, and T3, right? Now what we'll do, we will take what? Okay, we will take one particular volume. Let me extend this graph a little bit. Okay, right. So we will take one particular volume. Okay, and we'll take three different pressures now. Right, this is T3, right, because this is T3, right, and this particular value is P2, and this particular value, what I'm getting here, is P1. Okay, one constant temperature. So obviously now again, if I go from this side to this side, top to bottom, the pressure increases. P3 greater than P2, greater than P1, that we know, right? Okay, now look at this. Now we have a solid container. Okay, we have a solid container, and okay, that is, this cannot expand. Okay, this vessel cannot expand. This is like a steel vessel, something like that. Okay, now what we do, we are now going to heat it, right? We are increasing the temperature, right? So obviously what will happen now, if you take an individual gas molecule with a lesser temperature, they will have lesser kinetic energy, right? Now they will have more kinetic energy as the temperature is increasing. So they will go hit the wall of the container with greater force, with greater velocity, right? That particular individual gas molecule will absorb the heat energy and they will travel faster, right? They will travel faster. That means they will go hit the walls of the container like little more force. Obviously, little more force means little more pressure. So we can also say, again, this also you study in the form of a law, temperature and pressure at constant volume. Again, the volume cannot change, right? The volume cannot change. The temperature and pressure are going to be constant. I mean, directly proportional, right? So if T3 is the greatest, T1 is the least, definitely T3 should be the greatest and T1 should be the least. Same answer you're getting, same answer as in this case. Yes, okay.
Okay, sir.
Right, good. So these are the different kind of questions which can be asked from the graph, right? Very simple questions like this, and that is all about your Boyle's law. Okay, right. We'll move on. We'll move on to the second law, right? And that is Charles' law. Okay, the name of the scientist is Charles. Okay, right. So Charles' law, you can take it to the statement, people. Hey, Charles' law is pressure and temperature, or temperature and volume. I think it's temperature and volume, right? I forgot. 1 second, people. It is volume and temperature. Okay. Yeah, take the statement, people. Take down the statement for Charles' law. At constant pressure, directly proportional. Temperature of the gas is directly proportional to the volume of the gas. Right? This is directly proportional to the volume of the gas. Right? So let me repeat the statement again. Full statement: at constant pressure, right? The temperature of the gas is directly proportional to the volume of the gas. Very simple. Now again, that example which we already saw, right? If you just heat a balloon at one, say the pressure should be same. Okay, the pressure inside the gas, the pressure of the gas should be same, right? So obviously, if at all you want to keep the pressure same, you have to increase the volume so that the pressure releases, right? Because eventually, if you increase the temperature, the pressure will increase because the gas molecule will now have more energy. It will go hit the walls of the container with little more force, so more pressure should come, right? But what is doing now? Now we are increasing the distance between the gas molecule and the wall of the container, right? So even though it is going to go with so much force, since the distance is increased, when it is going to hit the initial pressure and this pressure, it is going to be exactly the same. right? That is why we are increasing the volume. But if the volume doesn't change, people, if the volume doesn't change, obviously the pressure will increase, because now it is going to be testing only the distance remains same. So obviously it will go hit with a greater force, with greater pressure, right? Okay, so that is what is told by Charles law. So we can easily tell that the pressure of the gas, the volume of the gas is directly proportional to the temperature of the gas, right? Directly proportional to the temperature of the gas. Or we can, if at all I remove the proportionality sign, I can write V is equal to some constant into T, right? Or we can also tell V by T is some constant value, or I can write V1 by T1 equal to V2 by T2, so on so forth. Vn by Tn is equal to some constant value. Okay, so at any particular point, you measure the pressure, you measure the temperature, you divide them. Second case, another pressure, another temperature, you measure them, you divide them, you're going to get the same value. That's exactly what is told by your Charles law, right? Okay, before we move on to this, I actually forgot one kind of graph which you can actually ask in Boyle's law itself, right? People, if I ask you, there is a graph between pressure and reciprocal of volume. Okay, pressure on the y-axis and reciprocal of volume on the x-axis. How do you think the graph will look?
Sir, could you repeat the question, sir?
I am plot. We saw the graph between pressure and volume. The graph was a rectangular hyperbola like this, right? Now I am drawing graph between pressure and 1 by V, not V, reciprocal of volume. Okay. Now how the graph will look? What will be the shape of the graph? Any guess? If at all you want to go for a wild guess, what it will be? Okay, fine. People,
So,
if you
will
do
it be
yeah, will it be
so like a curve from the origin?
curve? So, right. Let us look into this. Right, people, look at this. We say that the pressure is inversely proportional to volume, right? And we wrote this equation. Now, this equation, how can I write it? Like say, a little modify it. P is equal to K into 1 by V, right? P is equal to K into 1 by V, right? Okay. Now, does this look like any particular curve to you, right? Like what we did, we put pressure in the y-axis, okay, and 1 by V, this entire term in the x-axis, and there is some constant, okay, and that constant will be written as m. So if you get this kind of equation, this is equation of what kind of graph? Say if I get graph like y is equal to 2x, what kind of graph is it?
Linear
Sorry?
linear graph.
Yeah, straight line, right? Straight line. What is the equation? What are the different equations for straight line, people? Straight line equations. What are the different ways? Right? Y is equal to mx plus c. Again, you can even also have just y is equal to mx where c is equal to 0. Right? Or you have something like a slope point formula, something you have. Anyways, I don't want to go into the details. These two are the equations of straight line. Is it not? Y is equal to mx, or say y is equal to mx plus c, where the c is an intercept and the 0 in this case will become y is equal to mx, right? So what is this, people? This c is what is called as an intercept. Let me let this down, right? This c is what is called as an intercept, right? And what is this m called as? What is m?
Slope.
Slope. Right? So m, slope is nothing but m. So what is the formula for finding slope, people? How do you find a slope? Sorry, tan theta. Okay. If at all I talk in terms of coordinates.
y2 minus
Minus a.
y1 upon x2 minus x1.
y2 minus y1 divided by x2 minus x1. Right? That is the formula for finding your what is that? Slope. Right? What is intercept? Intercept is where when I keep x is equal to 0, what is the y value? That is what is intercept. Is it not? When I keep x is equal to 0, right? What will happen? Y is equal to c. Right? When x is equal to 0. Right? So what is the starting point of the graph is what is told by this. Right? Say, if I want to explain you, right, this is y-axis, some y, some x, right? Now, if at all I write y is equal to mx plus c, this is the graph. So this particular point where the graph starts, when x is equal to 0, right? What is the y value? C, right? And obviously, if you take the slope of this line, and this slope is nothing but m, that's okay, right? This is how the graph will look, right? Okay, now that's exactly what we're doing here also, right? Where is it? P is equal to k into 1 by v, which is nothing but y in the y-axis we have p, in the x-axis we have 1 by v. So this is like y is equal to mx. Okay, so if that is the case, where are you? Yeah, if that's the case, how the graph will look? It is definitely going to be a straight line. Okay, but where it should start from? Where it should start from? What is the value of c here? Right, we have p is equal to k into 1 by v, which is nothing like my is equal to mx. Right, now plus 0, right? What is the value of c? 0. There is no intercept, that means 0, right? So where should the graph start from? It should start from the origin. This is how the graph will look. Is it not, people? Are you understanding or not? Yes, no? I hope you are understanding, right? So it is like p is equal to k into 1 by v. That is the equation we have. This is like y is equal to mx plus c, where c is 0, right? I told you what exactly is the c, the starting point of the graph, starting point of the straight line. In this case, c is 0, so it is going to start with origin. Very simple, right? So this is how the graph will look for p versus 1 by v. This is how the graph should look. Right, now again I can ask you the same question. If at all I have graphs like this, right? Say, okay, fine, right? Something like this. This is T3, this is T2, this is T1. Now again, you will get the same answer as T3 greater than T2 greater than T1. The same thing you will get. Okay. Right. Anyways, don't worry about it. This is another kind of graph which you will be able to get. P versus 1 by v. Okay. Fine. So now what we have? Now we have Charles' law, which says V is equal to K into T. Right. Now remember that the temperature should always be in Kelvin. Okay, because that is the SI unit. We always take Kelvin temperature in terms of Kelvin. That is a unit which we'll use. Okay, even if they give you some other unit, Celsius degrees or Celsius Fahrenheit, you will try to convert that into Kelvin, then only do that particular question. Okay, right. So V is equal to K into T is what we have, or say V1 by T1 equal to V2 by T2, so on and so forth, all equal to some constant, right? Okay, now if I plot a graph between, say, temperature in the x-axis and volume in the y-axis, right? How will the straight line look like? Okay, I told the answer how the graph will look like.
Originally, sir.
Yeah, again, it's something like, again, it's very, very similar to okay, we can even write K is equal to, or if I write T is directly proportional to V, right? So T will be equal to K into V, whatever it is, or V is equal to K into T, whatever it is, something like this, right? So again, this is like what? Y is equal to mx. Again, the exact same thing what we are expecting, isn't it? But there is a small problem here, right? If you feel that the graph is going to look like this, you are not wrong, right? But there is a problem. As I told you, right? The temperature should be in terms of Kelvin, right? Now, what are you doing here? You are actually starting from 0 Kelvin. Is it not? Right? 0 Kelvin. Okay, 0 Kelvin is a problem. Okay, you will study again about this in depth in thermodynamics. Okay, thermodynamically, the nature does not allow you to go to 0 Kelvin. You cannot, whatever you try, whatever you do, right? You will not be able to reach this temperature, minus 273 degrees Celsius, or say 0 Kelvin. Cannot, a big no, it cannot be reached. Okay, it cannot be reached, right? If that's the case, we don't have anything called a 0 Kelvin as such. That's what you have to understand, right? That is absolute zero, right? That is a lot of things. You'll understand that the world ceases to exist. It will not even exist if temperature is going to go to minus 273. You understand why? Okay, so as of now, what you have to understand is this minus 273.150 Kelvin, you can close to absolute zero. You can go near it, right? But you cannot reach absolute zero, right? That is how nature works, right? Okay, so that means this graph is not possible, because this, according to this graph, we are actually starting with 0 Kelvin, right? So this is not the graph, right? How the graph should look, right? Temperature with respect to Kelvin and volume, the graph cannot start at 0 Kelvin, so it has to start somewhere from here. Okay, now if you extrapolate this graph, then this particular point is where I have 0 Kelvin, which cannot be reached. Okay, that is why we draw the straight line, right? But the actual graph starts with some other temperature, not 0 Kelvin, because 0 Kelvin cannot be reached. Okay, so this is the correct graph, what I'm giving you now. Okay, I hope you understand what I'm trying to say. 0 Kelvin cannot be reached, so you cannot start the listing from origin. Okay, you have to start the graph from some temperature which is not 0 Kelvin, little higher than 0 Kelvin. Okay, so that is how the graph will look. Okay, people, now I'm asking you, right? I'm giving you, okay, these kind of graphs, what we are getting, right? These kind of graphs, which are, say, there is something called as an isobaric process. Okay, there is something called as an isobaric process. These isobaric processes are nothing but constant pressure processes. And how we have isothermal process to be constant temperature process, right? In this case, what are we doing? We are making sure that the pressure is constant and we are changing the volume and temperature, how they are related. That's what I'm trying to study, right? So these kind of processes are what are called as isobaric process, which is nothing but processes happening at a constant pressure. Okay, and the graph which you're gonna get, right? This graph, whatever you got, this graph is nothing but it is called as an isobar, right? That means what? It is a graph which is obtained at constant pressure. Okay, isotherm is a graph which is obtained at constant temperature. Isobar is the graph which is obtained at constant pressure, right? Okay, now if I give you 3 different isobars, right? This is temperature, this is volume. So the graph starts here, here, and here. It's on some graph, something like this. Okay. Again, this cannot be a good graph. Let me put it like this. Okay. Right. So this is going to happen at, say, pressure P1. This is at pressure P2. This is at pressure P3. Can you arrange them in the ascending or descending order? Right? P1, P2, P3. Arrange them in the order of their ascending or descending orders. Go for it and tell me what is correct. These are isobars. 3 different isobars, 3 different pressures. What is the order?
Sir, P1 is greater than P2 is greater than P3.
Yeah, tell me, Suprajit.
P1 is greater than P2 is greater than P3.
So you are telling P1 greater than P2 greater than P3. Okay, fine.
Yes, sir.
Anyway, okay. Anybody else get the same answer or a different answer?
Same answer, sir.
Same answer. Okay. Anybody else? Okay, people, we again do the same thing. Make one thing constant, there is the other thing, right? Say, let me take maybe volume constant, right? Some particular volume will take, and we'll take three different temperatures. This is one temperature, T1, and this is your T2, right? And this particular temperature, what are you getting? Okay, it's not exact, but T3. Okay, P1, T1, P1, T1, P2, T2, P3, T3. Okay, right. So you understand that obviously this side the temperature increases, the graph is like that only, right? So we can obviously tell T1 greater than T2 greater than T3 for sure. And we know that the temperature and pressure are directly proportional. We already know that. We'll again see this form of law. That is your Gay-Lussac law. You'll see that. So we can also tell that the P1 is greater than P2, which is greater than P3. Okay. Right?
Sir,
Yeah, tell me.
sir, what if the linear lines are parallel to each other?
And that will never happen. Right? That will never happen.
No, sir, like they don't start from a particular point. Like they start from different points so that they are parallel.
Even if that's the case, you can do the same thing, right? You can do the same thing, right? Say, if at all you have graphs like this, parallel lines, right? Say now, but you have to choose the temperature very carefully. That's the thing, right? Say some temperature like this, or say some volume like this you choose, and then there are three different temperatures you can take and do this. No issues, you can do the same thing. Right, but this graph you will not get it like this. It will always start from one particular. What the understanding is, at one particular temperature, that particular volume will be only there, that for the particular gas, unless until you change the gas. Right, these kind of graphs you will not be able to get. Right, I would say these are graphs for different gases. Right, but these are for the same gas but at different pressures. Right, this is the kind of graph you will get if you use the same gas. Okay, right.
Yes.
So we understood that P1 is greater than P2 greater than P3. Right, now we can do the same thing by keeping, say, temperature constant and volume changing. We'll see what is going to happen. We'll see that also, people. Right, so we have one graph. Second graph. And why is my drawing skill so bad here? I envy people actually who have good drawing skills. Okay, cool. So these are the graphs which we get again: P1, P2, P3, right? And this is temperature and this is volume, right? Okay, now what we'll do, we will make sure that the temperature is constant and take three different volumes: V1, V2, and V3, right? And we know this side volume increases. So can I tell V3 is greater than, V2, which is greater than V1, right? And another relationship from Boyle's law, pressure and volume are inversely proportional. That means if V3 is the greatest, so P3 should be the least, right? And obviously P2 should be in between. And if V1 is the least, P1 should be the greatest, because it's exactly inversely related, right? So again, the same order you will get. Pressure, P1 greater than P2 greater than P3, exactly the same as here. Okay, right, people, that is about Charles' law, right? Done. We'll move on to the next law, which is there in our hands, and that is Gay-Lussac's law. Okay, right. Sorry. Right. So these are two scientists. Okay. Gay is one scientist, and Lussac is another scientist. Like, do not go for this. Right. So you don't have to associate gay to the sexual orientation of people. Like, these are common nowadays. You don't have to worry about it. Right. Do not laugh. Do not do that. Do not do that. Gay or lesbians are again simple people. They are people like us. Right. We are in a generation where we have to move past all that. Right, we should have some social acceptance, people. Right, so stop laughing. There is nothing to laugh. Right, there are also people like us, except that the sexual orientation is different. Right, Okay, so gay is another one scientist. This is a name actually. This is not representing sexual orientation people. Okay, this is one name, right? And another scientist is Lussac, right? So Gay Lussac's law we will study, right? You can take the statement. Please go on. Right. At constant volume, at constant volume, at constant volume, the pressure of the gas, is directly proportional. Right? The pressure of the gas is directly proportional. The pressure of the gas is directly proportional to the temperature of the gas. The pressure of the gas is directly proportional to the temperature of the gas. Right? Again, this is again an observation which we already know, that only if we're studying in form of a law. Right? Okay. So what is the mathematics behind this? It's very easy, right? So we say at constant volume, right? We're now keeping the volume constant. The volume cannot increase or decrease. No expansion or no contraction. Right? Okay. So if that's the case, we say that the pressure and temperature are going to be directly proportional. Right? The pressure and temperature are going to be directly proportional. Right? Now, this is again very simple. We already saw an example. What is going to happen if at all we have a closed chamber, like steel containers you have. Once you heat the gas, more faster, it is going to go hit the walls of the container and the pressure is going to change. Right? Okay, pressure is going to increase. Change means what? Increase. Right? Okay, so we can write P is equal to some constant K into T to remove the proportionality sign, or we can write P by T is constant. Right? Okay, then or I can also write it like this: P1 by T1 equal to P2 by T2, so on and so forth. Pn by Tn all equal to one particular constant. Okay, all equal to one particular constant, some constant, whatever be the constant is. Right? Okay, people. Now, if I draw a graph between temperature in the y-axis and pressure in the x-axis, right? Actually, you take this instead of take it as pressure directly proportional to T, you take T directly proportional to P, right? Anything works, right? Anything works, right? Why am I telling you like this is because, or you take both the graphs, doesn't matter, P versus T, or you take pressure versus T. Here, whatever it is, doesn't matter. You are gonna get to modify to just worship the same graph. Okay, that's all you're going to get. Tell me how both the graphs will look.
So the first graph will look the same as the previous one, the previous case.
Right? Previous temperature versus volume, right? Same, because again, the same temperature cannot be 0 Kelvin. So you have to start something somewhere from here. Okay. Now, how this graph will look then? You cannot start at 0 Kelvin. You have to start at some other temperature, and it is a straight line. So how it should look? Right?
So
I will just give you 5 seconds.
Somewhere from T, like from the x-axis, from the x-axis, but somewhere far away. Yeah,
that's it.
Exactly.
That's how the graph will look. Right? You should not start at 0 Kelvin. That's all I'm telling. That's it. Right? You can start on some other temperature. That's it. This is how the graph will look. Right? Okay, people. Right? That is all about this particular. What is that? Yeah, can I tell me?
Sir, you're telling that nothing can be at 0 Kelvin, right?
Nothing can be 0 Kelvin. No, we cannot reach 0 Kelvin.
Yeah. So,
yeah.
So will it be like at least negligible to 0 Kelvin or nowhere near 0?
You will be able to, like, see, I am not sure till now what is the maximum temperature they have reached, right? But I don't know, some years back I saw up to minus 269 they have went, right? Up to minus 269 they have went, right? But not more than that. That is the latest data I remember. But you check in your net, internet, right? Which is now the maximum least temperature which is reached. Okay, they might have improved, but again, you theoretically you cannot go to 0 Kelvin. Okay, you cannot go to 0 Kelvin. You can go up to that, but 0 Kelvin cannot be reached. Okay.
Okay, sir.
Right. Right. What is the time? Okay, 10 more minutes. Right. So that is about Gay-Lussac's law. Okay, people. Again, okay, we can have this kind of constant volume processes are what are called as isokoric processes, right? Isokoric process, right? And same way, the graph which you obtain here are what are called as isocors. Okay, these are what are called as isocors. Okay, so if I can give you 3 different isocors, again the same question can be asked, people. Temperature versus pressure. Now 3 different things. Say this is at volume V1, volume V2, volume V3. You will again get the same thing, right? You will get volume V2, V1 greater than V2 greater than V3. This is what you will get. You can if at all you want, you can check. Right? Okay, so that is about Gay-Lussac's law. Right? Now the fourth law. Right, the fourth law, we still now saw 3 laws, right? Boyle's law, pressure directly inverse proportional to volume. Charles' law, temperature, volume directly proportional. Now, Gay-Lussac's law says pressure and temperature are directly proportional. Now, the last one, which is going to connect the last variable, right? And that is Avogadro's law. Okay, that is Avogadro's law. Okay, now here what are we going to connect? We are actually going to take the number of moles. Okay, please take the statement, you'll understand. Take down the statement. At a constant temperature and pressure, right? Now, both pressure and temperature are constant. Okay. At constant temperature and pressure, the number of moles of the gas, is directly proportional. The number of moles of the gas is directly proportional to the volume of the gas. Right, now it's very simple, right? Again, I'll repeat the instruction one more time. Okay, so at a constant temperature and pressure, right? At a constant temperature and pressure, the volume of the gas, the number of moles of the gas is directly proportional to the volume of the gas. That's what it says. Right, now it is very easy, right? What do you mean by number of moles? The amount of gas, right? So at one pressure, at one temperature, say you add more amount of gas, more number of moles, obviously the more volume will be there. That is very easily understandable. But again, that is an observation made by the scientist Avogadro. We know something called as Avogadro number. All these things we have already studied. That guy, the same guy. Right? Okay. So we can now this was actually done in this number of moles itself, right? At STP, we say at STP, right? Now 1 mole of a gas will have dash volume. What is the volume? At STP, 1 mole of any gas will have any
liters.
Yeah, 22.4 liters. Right? Now you understand, right? At one constant temperature, right? Now we know the temperature is 0 degrees Celsius and pressure is 180. Right? Now, if at all I have this pressure and this temperature, if at all I have 1 mole of gas, that is going to fetch you 22.4 liters. So 2 moles of gas, now how much will have? Can I say it will be 44.8 liters? 3 moles will have 67.2 liters, something like that. Say 0.5 moles will only have 11.2 liters. So what are you understanding here? The volume and the number of moles are actually directly proportional. Right? We already know the relationship also. What exactly is the relationship? Right? So now that this 1 mole, 22.4 liters is that this temperature and this pressure. Right? But if the pressure is changed, temperature is changed, 1 mole of gas can occupy some other volume, but we don't know what exactly is that. Right? So that's why we say generally pressure and volume and number of moles are going to be directly proportional. Right? So we can write V is equal to Kn, or we can write V by N is equal to K, some constant, right? Or we can write V1 by N1, V2 by N2, so on, so forth. Vn by Nn is some constant value. That's it. That is what is called as Avogadro's law. Okay, so these are all simple observations done by different scientists given to you in the form of mathematical laws. right? Okay.
Sir.
Now what are we now what are we going to do in the next class? Next class we are going to do problems on all of these 4 laws. We will do again good problems, good interesting problems we'll do, right? And what are we going to do is we are going to combine all these laws and we are going to produce one most beautiful, most powerful equation for gases. Okay, we are going to combine Boyle's law, Charles' law, Gay-Lussac's law, Avogadro law. We're going to combine them. We are going to get one beautiful equation. Okay, and that equation is what is called as ideal gas equation. Right? Now, the most powerful equation for gases in chemistry or in science, in general, I can say. Right? We will see what is the ideal gas equation and we will do problems on that also. And with that, you'll be able to see what exactly is an ideal gas. Right? Now you understood that there are going to be 4 laws. Okay. Now, for a gas to be called as a perfect gas, right? All these 4 laws should be obeyed. On top of that, we will give more insights of what are the other qualities. Right? There is actually a theory called as kinetic theory of gases, which will tell you, okay, if at all you want to call a gas an ideal gas, these are all the qualities it should possess. We'll see all of that. Okay. So next class, that is tomorrow's class, I guess, right? Tomorrow's class, we'll do some amazing problems based on all these 4 laws, and then we'll move on to ideal gas equation, and then we'll move on to problems. And if at all we have time, we'll look at the other properties. What are the properties of a gas which should make it ideal or perfect? All those things we'll understand. Okay. Any questions anybody has? Any particular question anybody wants to ask me? Right? Okay, I suppose there are no questions, right? So I think we can stop right here. Right? Okay, people. Thank you so much. We'll meet tomorrow. Right? I'm ending the class.
Thank you, sir.
Thank you, sir.
Thank you, everybody.